Hello बच्चों, सत श्री अकाल and namaste from my side. How are you all? So we are here with the second lecture, right? We are here with the second lecture of electric charges and fields, or in another sense electrostatics, right? So in this, right, very simple thing is going to right happen here. Today, yesterday it was fundamental lecture. Okay, we did in small things. But today we are going to move forward for the most important laws of the electrostatics, that is Coulomb's law. Right? Something that appears in front. First of all, I want to tell you lots of visualizations are going to come. Lots of live demonstrations are going to come. Lots of funny examples related to the day-to-day life are going to come. As you have seen, as you have seen into the previous lectures, right? Generally, the 11th physics is more relatable to the day-to-day life, right? It is more relatable to day-to-day life, but it's okay. We are also going to relate that 12th part. Okay, you are going to enjoy, I guarantee. So you can say the approach matters. This is just a fun. Okay, because there is an analogy between the Newton's law of gravitation and the Coulomb's law, right, for electrostatic force. Okay, there is the analogy, they are a similar kind. The Newton's law of gravitation is associated with the mass, while the Coulomb's law is associated with the charge. And this thing we have explained into the previous lecture also, that like analogous to the mass, the charge is also the intrinsic property of the matter. Charge is also the intrinsic property of the matter. Okay, and this side positive repel, negative repel, positive attract each other. So this kind of funny things is there. Okay, as I always used to say, physics is not as horrible as you all are thinking. Okay, or you all are judging by the cover of the physics book. Okay, no, it is just not represented well. The one who have represented well, okay, that part, okay, he is now with double inverted. His name is written with double inverted. Okay, so we are trying to we are trying to represent the physics as much into the simplest form as much as right possible. Okay, so what will be the agendas of the today's lecture? We are going to cover up, right, the Coulomb's law. Okay, Coulomb's law. I'm sorry, it went overlap. Extremely sorry. Okay, this is the second lecture. Coulomb's law. Right? How sums are asked into an examination, what actual the Coulomb's law states, how we can represent, like what are the limitations of the Coulomb's law, how we can represent it into the vector form, how to overcome the limitations, okay, what will be the live demonstration of it, right? Lots of things we are going to discuss. Before moving on to the Coulomb's law, students, please make sure, okay, please make sure that you are completely aware of all of those fundamentals that has been discussed into the previous lecture. All of those fundamentals that has been discussed into the previous lectures, please take a note of it. You should all be aware of. Else nothing you are going to understand in this chapter, because electrostatics is a different part and we have to move on to that into the very different way. Okay. So today we are going to deal, here is a visualization, we are going to deal with the Coulomb's law. Okay, the reality of the Coulomb's law. Okay, the reality of the Coulomb's law is about two charges. Right? Charges are generally, this is a reality in another sense, we are going to give you all a very basic information about it. Two charges, one is a positive charge, second is a negative charge. One is a positive charge, second is a positive charge, second is a negative, the first one is a negative. Okay, there exists a kind of force between the two stationary charges. There exists the kind of force between the two stationary charges. Let us take an example. Now we are directly moving, without wasting the time, we are directly moving forward to the Coulomb's law. You can see in this visualization, right? Here is charge 1, here it is charge 2. Okay, they are separated by some distance r. They are separated by some distance r, right? I think the white pen is not visible. Okay, this is charge q1, this is charge q2. They are separated right by the distance r. If they are separated by the distance r, why they are moving like this way? Okay, first when experiment was done, the positive and positive charge, right, were kept near. It doesn't mean that we are picking one positive charge like a button and another positive charge like a button and we are keeping near and we are trying to conduct an experiment. No, extremely not. Okay, this was done at the very microscopic level and this is just a visualization in front to understand the topic, right, well. Okay, when the experiment was done at the microscopic level, it was right hands observed that when two positive charges are kept nearer, they are repelling each other. Okay, the same happens when the two negative charges are kept, okay, near to each other. While if we are contradicting it, if we are contradicting the repulsion, then when the positive and the negative charges are kept at some distance, right, then they saw the kind of the attraction is going on. So what is the result behind? When two positive charges are kept near, right, they are going to repel. They were moving apart. And when two opposite charges were kept at some distance, they were moving near to each other. So the scientists gave the right explanation what was the actual reason behind it. Same we are going to see. Suppose this is charge Q1. Suppose this is charge Q2. They are right separated by the distance r. The first, that is charge Q1, second, that is charge Q2, and they are separated by the distance r. Okay, when they both are separated by the distance r, then what happens here? Right, depending on the nature of the, see, first of all, the compulsion thing is charges are stationary. Right, charges are at rest. Okay, the both of the charges are the rest. Depending on the nature of Q1 and Q2, depending on nature of Q1 and Q2, right, the attraction and repulsion will occur. Okay, depending on the nature of Q1 and Q2, the attraction and repulsion and occur. Right. So here comes the Coulomb. Okay, he stated that, right, Coulomb stated that the force attracting between the two stationary charges, they are defining it as an electrostatic force. I can't say it is only the electrostatic force of attraction, but just as the electrostatic force. So the force is directly proportional to the product of charges and inversely proportional to the square of distance between them. This is nothing else but the Coulomb's law. So they observed, right, this kind of the attraction and repulsion is going on. So as per that, they gave a law, right? So whenever the two stationary charges are kept at some distance, right, so there exists an attraction or repulsion between them. Right, this law is also known as inverse square law. This law is also known as inverse square law. Why it is also known as inverse square law? Because here F is, right, inversely proportional to r square. Okay, F is inversely proportional to r square. Right, and lots of reasons are there behind being an inverse square law, but right now we are not moving on to that part. Okay, here we are directly moving on to the very simple explanation. The attraction or the repulsion between the two charges kept at some distance apart is represented through force, right, and that force is F, electrostatic force, and that is K Q Q1 Q2 whole divided by r square, where K is the proportionality constant, right? K is the proportionality constant. So this is very simple thing, right, what the Coulomb's law is all about. Okay, without wasting our time, we are directly move on to the what is an actual value of the K. Okay, now this is a scalar form. Why it was necessary to introduce the vector form? First of all, we are going to cover up the entire theory of the Coulomb's law, right? And then we are going to move on for 10 to 12 examples in this session. Okay, and 1 to 2 examples within it, I will give you all as an homework. Right? I will give you all as an homework. So now what is the scalar form of it? Then how to define the direction of that force basis on the repulsion and attraction. This is an important part. Right? Student always used to get confused into it. Okay, student always used to get confused into it. Right? Suppose here, can I name it as charge number 1? Can I name it as charge number 2? Right? 1, 2. So there exists the force of repulsion between the two positive charges. There exists the force of repulsion between the two positive charges. So here, this charge is going to repel this. The force of repulsion is like this way. Right? The force of repulsion is like this way. Now suppose here if positive and negative charges are attracting each other, can I say the force of attraction is like this way? Again here, the force of repulsion is like this way. Okay. Now, how we are going to define whether which force is acting on which particle? The scalar form. See, we are going to see into the later part that why it was necessary to introduce the vector form. For first of all, we are going to clarify the each and every aspect of the scalar form. Right. So, what does the scalar form says? F that is equivalent to K Q1 Q2 whole divided by R of square. Right. F is equal to K Q1 Q2 whole divided by R of square. This is what the scalar form states. Now see, can I say if it is named as 1? Here, this is force acting on. Is it right? This is the most confusion, right, for all of the students, that whether, right, in which direction the force is going to act. Right? In which direction the force is going to act. Okay, so it's a very simple thing here in this direction. Okay, suppose if I am fixing this charge, right, then this charge is obviously going to repel into the opposite direction. So can I say the force acting on 1 as because of 2 will be in this? And suppose if I am fixing this charge, right, if I am, okay, fixing this part, okay, then this will be the force acting on 2 as because of 1. This is how the directions are identified. Okay, this is how the directions are identified. Suppose if I am fixing this part, then obviously this is going to attract. So can I say this is force acting on 1 as because of 2? Direction differs. Similarly, force acting on 2, right, as because of 1. Right. So this is how the directions are defined. Now, as Newton said that forces always occurs into the pair. As Newton said that forces always occur into the pair. So it means that these two forces, whatever they are, right, see, suppose the attraction is there or the equivalent repulsion is there. So they are equal in magnitude and opposite in direction according to the Newton's law. So if I am going to write down into the scalar form, if I am going to write down this thing into the scalar form, then I must say simply as F12 that is equal to negative of F of 21. Right? F1 of 2 that is equal to negative of F of 2 of 1. Right? Now here, it is important to understand the value of K. It is important to understand the value of the K within the Newton's law. Right? Now we are going to do that part. What will be the value of K? Generally, the K is defined. If I'm talking about the vacuum, if two charges are kept into the vacuum, right? If two charges are kept into the vacuum, then simply, right, K is defined as 1 by 4 pi epsilon naught, where epsilon naught is permittivity of the medium. Permittivity of the medium. Yes, it matters. What I'm going to say, yes, it matters. Generally, we have heard into the, right, we have learned into the gravitation part that medium is not going to affect the gravitational force. Okay, medium never affects the gravitational force. Medium never affects the gravitational force, but here the electrostatic force gets affected by it. Okay, so medium never affects the gravitational force, and being mass is positive, the gravitational force is always attractive in nature, but here the electrostatic force is affected by the medium. Electrostatic force, right, is affected by medium. How it is going to affect by the medium? How the permittivity plays an important role? How the relative permeability comes? Right? Okay. See, it's a very simple thing. First of all, we need to understand the permittivity of the medium and its respective value. Okay, if I'm talking about the value of K, then it is equal to 9 into 10 to the power 9. Right now, I'm not moving on to the units, it's SI. If I'm talking about the equation, the value of the permittivity, that is 8.85 into 10 to the power minus 12 S of I. Right. Near about values are there. Okay. Sir, how you can say it is near about? Okay, one is 10 to the power 9 and second is 10 to the power minus 12. Yes, it happens, it's okay. Okay, but by seeing all of those values, one kind of the, right, the synchronization, right, everyone fails. Okay, so here the most important, what is in actual the permittivity of the medium is all about. Permittivity of the medium is all about. The permittivity of the medium states, right, how medium is, see, in generalized form, I'm telling you all, I'm not moving on to that much technical part. How medium allows, right, two charges to attract or repel depending on the nature. How medium allows? Sometime it happens na, society is against hamara pyar. Sometime it happens na, she is against my pyar. ठुकरा के मेरा प्यार मेरा, like that ना. अब तो IAS बन के रहेंगे बाबूजी, जितना वो कमाती है मेरी गाड़ी उतना हफ्ते में तेल खाती है, राइट, मेरे पास घर है, पैसा है, गाड़ी, राइट, ठुकरा के मेरा प्यार मेरा इंतकाम देखेगी. हाउ मीडियम इज अलाउिंग, हाउ मीडियम इज परमिटिंग, राइट. It means anyhow, if here permittivity is there, right, if here permittivity is there, so it means somewhere the medium plays an important role. Permittivity is there, medium plays an important role. ठुकरा के मेरा प्यार. Okay, now lots of common love stories are going to come. Okay, if you are seeing all of those Bollywood films, right, okay, then always you can see, again, love stories, girl and boy, right, went on being a villain, society went on being a villain, right, two countries went on being a villain. Okay, now all of those villains into the love stories are covered and they are even repeated. Okay, so it depends on how villain allows girl and a boy to meet. जा सिमरन जी ले अपनी जिंदगी, like that way. How medium allows, it is an important part. Value of the K doesn't matter, epsilon naught, yes, this value changes with respect to the medium. Sir, first of all, you told that, right, this is a constant, right? As you told that K is a proportionality constant, and according to this formula, right, if K is proportionality constant, then there is a possibility, not there is a possibility, but we are for sure that epsilon naught is the constant. But how you can say the value changes with respect to medium? I said value changes, right? Okay, but the name also changes. Okay, this is the permittivity of the free space. Again, I am correcting myself why I have written this thing here. Some students might be right confused. Permittivity of free space or vacuum. Right? If this thing is gonna change, then here comes the permittivity of the medium. Permittivity of the medium. Right? Permittivity of the medium. So here if I am talking about the Coulomb's law, okay, let's understand. Here we understood the Coulomb's law into the scalar form. We identify the value of the K. We understood what actually the permittivity of the free space is. But now what happens when two charges are immersed inside the fluid? Right? When two charges are immersed in somewhere else area, in another medium, what happens, right, when they are kept, okay, in some specific medium? What occurs in that? If it would be the gravitational law, see, but this kind of the theoretical questions always comes up into an examination, because the one who designs that paper, he is aware of, okay, that you are not, okay, you're not knowing the basic difference between the Coulomb's law and the gravitational, the Newton's law. Newton's law, in the Newton's law, the gravitational force does not depend on the medium, while into the Coulomb's law, yes, it depends on the medium. Now let's take an example to understand. Suppose two charges right are immersed inside the fluid. Right, I'm not bounding those things. Physics is not right to bound that stuff. I'm writing, okay, rather than to bound it up, okay, let's write it as inside the medium, another medium than the free space. Right, another medium than the free space. Again, they are separated by the distance r. Okay, this is charge q1, this is charge q2. Okay, now the medium is having the dielectric constant K. What is a dielectric constant K? How we can correlate this to the permittivity of the free space and the permittivity of the medium? K is a dielectric constant. This is what an actual difference between the one-shot lectures, right, and the small regular lectures. Okay, in one-shot lectures, what happens? Entire content we are giving you all. Okay, it happens na. Suppose let's take an example. If I'm moving on to a restaurant having an unlimited meal, like that, unlimited meals, right? Suppose one restaurant is saying unlimited meals, khao, right? But human is having right only capability, right, to consume 300 to 400 grams of food. Okay, if we are saying, let's say someone is having capacity to consume 600 to 700 grams of food, right? Okay, then you are great. Unlimited ka paisa vasool kar loge, right? You are great. But here, what I am going to tell you all, right? What was the purpose, right? Okay. What was the purpose? How the value of the K we can associate with the, right? How the value of the K we can associate it with the permittivity of the medium and the free space. K is nothing else but the dielectric constant. How the value of the force changes with the medium, right? Okay. So see, suppose if I'm talking about the value of the k, then we are saying 1 by 4 pi epsilon 0. This k is different and this k is different. This k is into the upper case. That is k of dielectric constant. Okay. This k is like this into the lower case. As of this contradiction, generally in NCERT, they would never use this variable. All of those time they are using 1 by 4 pi epsilon 0. Because students always used to get confused into it. So it's k 1 by 4 pi epsilon 0 into the free space. And if I'm talking about the permittivity into the respective medium, then we are having k dash, that is equal to 1 by 4 pi epsilon naught, the permittivity of the value of the k into the medium. Okay. Suppose, let's take an example, Okay, let's find the value of the force. Okay, let's find the value of the force. Now, when the charges are kept into the free space, what is a force? That is equal to k q1 q2 whole divided by r square. When they are kept into the medium, the force is F dash, that is equal to k dash q1 q2 whole divided by r square. Replacing the value of k dash q1 q2 whole divided by r square, k dash, it is 1 by 4 pi epsilon naught, or you can say 1 by 4 pi epsilon. Can I consider this as equation number 1? Can I consider this as equation number 2? Taking ratio of 2 by 1. So F dash by F, okay, it is k dash by k, so this is going to come upon as F dash, that is equal to F by capital K. This k is of dielectric constant. This k is of dielectric constant. Okay. So if I want to define the value of the k, then dielectric constant is defined as a ratio of a permittivity of a medium to the free space. Ratio of permittivity of the medium to the free space. Simply I can define it as k, that is equal to permittivity of the medium with respect to the permittivity of the free space. This is nothing else but the dielectric constant. Okay, dielectric constant. So this is the value of the force with see, suppose if those two charges, if the system is kept into the medium, then this is the value through which the electrostatic force changes. Force into the medium, force into the medium, that is equal to force when charges are kept into the vacuum or the free space, whole divided by k, where k is the dielectric constant. The capital K and the small k differs. The capital K and the small k differs. Capital K and the small k differs. Let's have the live demonstration of the Coulomb's law. Then we are moving forward to the we saw the scalar form. Then we will move forward to the some of the limitations, the vectors form, then limitations. Then we are going to see how the limitations are being overcome. How limitations are being overcome. See now, these are the two charges present in front. These are the two charges. Right now I have not given the nature of the charges. Okay. This is 0 and 0. Suppose if I am going to give you all the 8 microcoulomb, I have given the charge of 8 microcoulomb to both. Okay, positive. See, that's why they appeared to there. Now suppose if they are kept at the distance of 3 to 7, the 4 centimeter. Then how much amount of the force it is acting? 3.6 into 10 to the power Newton. This is force acting on 2s because of 1. How we are going to identify this direction? Fix this part. Force acting on 2 is because of 1. Fix this part, force acting on 1 is because of 2. Equal in magnitude and opposite into the direction. Equal in magnitude and opposite into the direction. So first of all, again, let's see. Okay, okay, there is another simulation. Let's see that part. Charges and fields. Yes. Okay, there is another simulation. I think this is also going to help us to understand the concept of. Okay, yes, okay, this is the one. Okay, but this simulation we are going to more use into the while understanding the concept of the electrostatic potential difference. First of all, potential like thing never exists. Okay, when we'll understand the concept of potential difference, the relation between the potential difference and electric field. Okay, see now. It is going to attract. See, it is attracting. See, you can just imagine this is attracting. See, I'm going to take nearer. Okay. See, it repels. It repels. Okay, if one is able to see this effect, see, it repels. See, it repels. Right. Okay. So these two are the positive charges if I'm moving on to the sensors. Right. Okay. This is the direction of the net electric field. Okay. See, this is the direction of the electric field. Okay. But this thing we are going to discuss into the, what we can say, I told you all into the potential difference and all. Right. Now there is a possibility in between these 2 points. If they are of the same nature, then there exists a point in between 2 where we are having the net electrostatic force as 0. To understand the concept of net electrostatic force as 0, right, one test charge is needed, and it is important to understand the superposition principle, right, and the vector form of it. The superposition principle and the respective vector form. Okay, so now let's move on to it. Let's, without wasting our time, okay, directly we are moving forward to the limitations of it. Okay, we are moving forward to the limitations of it. Basically, there are 2 limitations of the Coulomb's law. First, only applicable in between 2 charges, and for compulsion they all should be at rest. Only applicable in between the 2 charges, and for the compulsion they all should be at rest. Right? Okay. You can see into the visualization what happens, right? Coulomb's law fails, right, if more than 2 charges are present within the system, and even Coulomb's law fails when 2 of the charges, suppose if I'm talking about the 2 of the charges but they are moving with some specific velocity, it means somewhere the magnetic field is involved and there is a possibility for a charge to produce an EM wave, right? So in that case it is a very simple thing, right? The Coulomb's law fails. So it is only applicable for the charges those who are at the rest, okay, and not more than 2 charges. Even this is not applicable for the continuous bodies. It is not even applicable for the continuous bodies having charge uniformly or non-uniformly distributed over them. Uniformly or non-uniformly distributed over them. This is not applicable between the point charge and the sphere. It is not even applicable between the point charge and the rod. So the rod that is having a charge, whether uniformly or non-uniformly distributed over it, we are not interested whether it is uniformly or non-uniformly distributed. The simple thing is all about if it is between the continuous body having the charge distribution over it, then the Coulomb's law fails. These are the two most important, right, limitations of the Coulomb's law. See, charge distribution, like you can see in this visualization. Okay, this is how, right, a continuous body is made having the uniform charge distribution or the charge distribution over it. Okay, the body is made having the charge distribution over it. Yes or no, guys? And this is how, if n number of the charges. So we are going to overcome this limitation, right? If you want to calculate the right value of the force, right, okay, to overcome the limitation, then we are having the superposition principle, right? And if you say, is it not possible that in the entire universe only two charges are present? No. In the entire universe, is it possible that only two charges are present? No. In the entire universe, this is possible that only your one love story exists. ठुकरा के मेरा प्यार मेरा इंतकाम. So for our subscribers, those who are into the watching this lecture into the pure English mode, sorry, I never used to hear all of those Western songs, right? मैं नहीं सुनता. I never used to hear even Bollywood songs, but generally whenever right, my family is used to scroll all of those TVs and this kind of the songs, yes, it strikes, right, and fits. Okay. So to overcome the first limitation, we are having the superposition principle, and to overcome the second principle, right, we are having the concept of the electric field. If you want to calculate the electrostatic force in between the point charge and the continuous body, right, for having the uniform or non-uniform charge distribution over it, right, somewhere the electric field needs to be involved. And if you want to calculate the resultant force into the charges on a specific charge into the system that contains n charges, then the superposition principle is there. I'm not saying that exactly the limitations of the Coulomb's law are covered through these two concepts, no. But we are going to see that into the different way. Let's move on to the Coulomb's law into the vector form. Okay, let's move on to the Coulomb's law into the vector form. See, is it possible that two charges into the universe are only distributed into, or they're only placed on to the one dimension under the single line? Is it possible? It can be anywhere into the three-dimensional space, right? Charges can be anywhere in three-dimensional space. Right. So for that reason, see why, first of all, before moving on to the purpose of this, right, the vector form of the Coulomb's law, just understand the purpose of introducing vectors into it. Purpose of introducing vectors. Physics is all about to understand whatever the natural phenomena or whatever the phenomena, the study of phenomena, right, that are going on into the surrounding. All of those phenomena are going on into the single line. Is it possible that all of those phenomena they are on the rectilinear path? Man can only walk onto the rectilinear path. He can't even move on to this or this straight path. No. So as of that reason, to represent all of those physical quantities into the physics that depends on the direction, that changes with respect to direction, the concept of vectors were introduced. Why vectors are there? If you want to represent something into the xy, into the xyz, right, the vectors are needed. Okay, so charges can be anywhere into the three-dimensional space, right? So as of for that reason, see, suppose this is charge number 1, this is charge number 2, obviously they are going to repel. Suppose this is an origin, right? Okay, there are some characteristics of the Coulomb's, or you can say this electrostatic force. Okay, the most important thing that I'm going to write, but that thing is not explained into the scalar form. It is must to explain into the force between two charges always acts on line joining between them. It always acts on line joining between them. Distance between two charges are with respect to their centers. With respect to their centers. So these are the two most important noteworthy point in another sense, the characteristics of the electrostatic force. Indeed, you have to take a note of it. Right, as I used to say into my previous lecture, please have a notebook and pen with you all. This is a mandatory thing, right? Into the previous presentation slide, the limitations were the mandatory thing. So I want you all, right, okay, to immediately note this down. I'm moving aside. Just pause this video and immediately note this down. Right, guys? And those who have noted down, kindly please comment box into the right comment beneath the video, please. Okay, this is the one and this is the second. Please note this down. Okay, so yeah, this is 1, this is 2. If I'm fixing this, force acting on 2 is because of 1. If I'm fixing this, right, force acting on 1 is because of 2. Right, so they are separated by the distance r. Na? Suppose position vector of the first charge is r1, position vector of the second charge is r2. Can I say this as we are in need of this distance, as because they are right having, right, the first charge particle is at the position r1 into the three-dimensional space. The second charge particle is at the position r2 into the three-dimensional space. So as of that reason, simply I am telling you all, we are in need of that kind of, we are in need of what we can say, right, the distance, that is exactly the line joining between that. So how this Coulomb law is represented into the vector form? Suppose if I'm talking about the force acting on 1 is because of 2, right? So that is K Q1 Q2 whole divided by R1 minus R2 square. If this is represented into the vector form, then obviously it might be having the direction. So that direction is represented by unit vector. Direction is represented by unit vector, right? So if I'm going to say this F1 and 2, then it is defined as K Q1 Q2. If I'm elaborating this term, then we are having R1 minus R2 whole of cube, and that is a vector R1 minus R2. The definition of the unit vector that you all are aware of, you have seen into the fundamentals. Vector divided by its magnitude. Vector divided by its magnitude. K Q1 Q2 R1 minus R2 whole divided by and if you want to write down F12 into the vector form, that is negative of F of 21. And if you want to really write down distance in terms of the magnitude, then F1 of 2, right, that is equivalent to F2 of 1. Right? This is how the Coulomb's law into the vector form is represented. Okay. Now, if I'm moving aside, right, I'm moving aside on the countdown of 10 seconds. If you want to note this down, right, you can on the countdown of 10 seconds. Okay, on the countdown of 10 seconds. Come on, everyone. Okay, now two most important principles are remaining. Superposition principle, its respect to scalar and vector form. Okay, and after that directly we are moving forward to the sums, and the concept of the Coulomb's law will be over. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's it. Examples, it's okay. As I told you all how limitations are covered. Okay. Now, superposition principle, to cover the first limitation. What happens when more than one charges are present into the system? Or in another sense, the n number of the charges are present into the system. N number of the charges are present into the system. What happens? The n number of charges are present into the system. See, it is not possible to calculate the interactive electrostatic force between all of those two charges, all of those n number of the charges. It is not possible to calculate the net electrostatic force, the net interactive electrostatic force in between all of those charges, but it is possible to calculate, right? It is, mark my words please, it is possible to calculate the net or the resultant force on individual charge the force on the individual charge S of n charges in system. Again, I am saying it is not possible to calculate, right? It is not possible to calculate because Coulomb's law fails. See, n number of charges are present. Coulomb's law fails. Then how superposition principle is going to overcome its result? Its limitation. How superposition principle is going to cover, right? It's going to overcome its limitation. How? It's a very simple explanation, my friends. Very simple explanation. N number of charges are present. We are not able to calculate the interactive force, but select any reference charge from all of those n number of the charges. Select any reference charge. On that reference charge, you can easily calculate the electrostatic force, the resultant electrostatic force. Suppose if I am naming it as a 1, this is 2, this is 3, this is 4, this is 5, and this is n. Step 1, to apply the superposition principle, there are some steps, right? Okay, first, select the reference charge. Okay, this completely depends on, right, your choice, which one you want to select. Suppose if I want to select S3, this is my reference charge, and I want to calculate the resultant force on it. So the resultant force on, right, that is F1 acting on 3, right? This is force acting on 3 as because of 1, right? This is force acting on 3 as because of 2. This is force acting on 3 as because of force. This is force acting on, right? See, right now I'm taking into generally the directions needs to be considered, but into the scalar form, if you don't want to follow that much complex approach, right, then in scalar form directly. Why it is a scalar form? Because all of those are right, all of those, right, are arranged, all of those charges are arranged into the single line. Okay, so rather than move on to the directional approach, okay, directly you can move on to the scalar. Select the reference charge, apply, right, the Coulomb law for individual. So this is force acting on 3 as because of 1, force acting on 3 as because of 2, force acting on 3 as because of 3, force acting on 3 as because of 4 dot 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 plus force acting on 3 as because of n. Force acting on 3 itself is 0. Force as because of 3 on 3 is 0. So f of 3 into the scalar form is f of 3 of 1, f of 3 of 2, f of 3 of 4 dot 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 plus f of 3 of n. If you want to further represent this thing, then it is k q3 q1 whole divided by r31 square. R31, it means distance between 3 and 1, plus k q3 q2 whole divided by r32 square. R32, it means distance between 3 and 2, plus dot 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 k q1 qn whole divided by r3n square, like this. Any of the reference charge you can select and you can represent it stuff. Any of the reference charge you can select and you can. So this is how the Coulomb's law is represented into the scalar form. Superposition principle, sorry, not Coulomb's law, superposition principle into the scalar form. Now what happens? Is it possible that in all of those cases, all of those n number of the charges are represented or are kept or positioned under the single line? Nakure. Is it possible that all the time they are going to position at the single line? Yes or no? Is it possible? No, na. Is it not possible? And superposition principle into the vector form comes. It is a very simple. If you are able to understand the Coulomb's law, write the Coulomb's law into the respective medium, okay, then easily you can understand this stuff. Apart from this, some of the important question. See, from here, right, from this resultant force, okay, always new thing comes of the equilibrium, right? Always a new thing comes up into the equilibrium. When two charges are kept and another third charge is introduced, and we have to check it out whether it is into the static equilibrium, right, neutral equilibrium, or what kind of this thing. Whether it is going to perform SHM, okay, but this is a different thing, okay, that we are going to see. See, separate practice question based session is kept. Separate practice based question session is kept. In each chapter, minimum 2 number of separate practice question sessions will come up, right? So in regular lectures, we are going to cover the each and every part of the concept, some of the important sums based up to NEET level we are going to see. But if I'm talking about those separate sessions, right, then we are going to see some of the critical thinking sums, some of the mixed concept sums, some of the advanced based sums I'm going to introduce. Lots of things we are going to discuss, right? Lots of things we are going to discuss, right? So how equilibrium we can correlate to the resultant or the net force, that we are going to discuss into the practice session, not at the beginner's level. Suppose this is charge number 1, this is charge number 2, this is charge number 3, this is charge number 4. Now, if you want to represent this superposition principle into the vector form, indeed direction is included. Select the reference charge. Select the reference charge. I have selected 2 as the reference charge. Why I have selected 2 as a reference charge? But it is easily to write to show you all in directions into it. Suppose if I am talking about 2, right, this is force acting on 2 as because of 4, right? This is force acting on 2, right, as because of 3, okay, 1. This is force acting on 2 as because of 1. All are represented into the vector. This is R1 of 2. This is R 2 of 4, right? This is what? R2 of 3. We need to calculate the resultant force on it. Now apply this equation, right? So can we say it is the resultant force acting on 2 into the vector form, that is force acting on 2 as because of 1, force acting on 2 as because of 3, plus force acting on 2 as because of 4. There is a possibility that n charges may be present into the system, but right now we are only trying for the 3 to 4 charges, right? Evaluate this. The resultant force on the 2, that is equivalent to K Q2 Q1 whole divided by R2 minus R1 whole cube R2 minus R1 plus K Q2 Q3 R2 minus R3 R3 whole cube plus K Q2 Q4 R2 minus R4 whole divided by R2 minus R4 whole cube, right? It is very easy, right? Approximately 1 hour we took to understand the Coulomb's law, its limitations, its characteristics and everything. Yes, approximately 57 minutes, right, of this lecture we have covered. Now rest of the time we are going to see, right, how the things are gonna happen. Okay, rest of the time we are going to see how things are gonna get happen, right? Please okay, then it's my instruction to you all, please be attentive, right? It's my instruction, right? Okay, to you all, please be attentive. Okay, please be attentive. Please watch this classes regularly, else you are going to get stuck in between. Okay, now let's move on to that part. Okay, first of all, let's revise this. Sorry, my slider is not working. Okay, we have started with this meme as usual, right? We have started with this meme as usual. Okay, please allow me to drink the water. Just hold on, right? I'm coming up, please. Okay, till then, okay, you can revise it, please. Okay, we moved on to the Coulomb's law, the value of the K, the permittivity of the free space and the medium, the limitations, right? Examples, it's okay. How limitations are covered, that is by superposition principle, right? The second, right, how the second limitation is covered. But before that, let's move on to the, first of all, let's move on to the, right, the sum of the important sums based on the Coulomb's law. Otherwise, this session is going to be null and void. Okay, the agenda of session is not only to, right, teach up the concepts into the most appropriate, into the convenient manner. No, the agenda of the concept is that more than 8 to 10 sums immediately they should be explained with this concept, so that, okay, it should get stored into the permanent memory of the brain. It can be stored into the permanent memory of your brain. Yes or no, guys? Right? So now, what does this example states? Q1, that is 4 microcoulomb. Q2, that is equal to 2 microcoulomb. They are separated by the distance of 10 centimeter. Two same charges of the same nature separated by the distance of 10 centimeter. Right. The question asks at what point or at what distance from 4 microcoulomb the net force is 0. Or another sense, it is also asked where the third charge capital Q should be kept from the 4 microcoulomb so that the net force acting on the Q is 0. The first statement is framed like this way into the question, and second statement is framed like at what distance from either 4 microcoulomb or 2 microcoulomb the net electrostatic force is 0. Now this question can be resolved from the regular pure imandari wali method, and it even can be solved through shortcut is but first let's solve this with imandari wali method, right? We need to check it out the point. Suppose this is a point at the distance x and this is 10 minus x. At the x from first charge, the net electrostatic force is going to get 0. Here, this is force acting on 3s because of 1. This is force acting on 3s because of 2. Let's name it 1, 2. See now, the net force on the 3, that is equal to force acting on 3s because of 1 plus force acting on 3s because of 2. This net force is 0. This is what's been said into the question. So can I say this is k q3 q1 whole divided by x square minus k q3 q2 whole divided by 10 minus x whole square. Why I have taken as a negative sign? Because into the direction they both are into the, or you can say both are into the opposite direction. So k q3 q1 whole divided by x square, right, and plus that is equal to k q3 q2 whole divided by 10 minus x whole of square. q3 is going to get cancelled, right? So this is 1 by x, that is under root of 2 by 10 minus x, right? Under root of 2 by 10 minus x, right? So 10 minus x, that is equal to root 2x, right? So 10 is equal to root 2 plus 1, right, of x. What is the value of the x that is coming out as? Right, approximately it is 3.7 something, 3.68 something, approximately, huh? I'm not moving on to the exact answers, right? Else, if you want to note this down into this format, it's okay. Right? Yes or no? Okay. So this is how the point we can evaluate this point. See now how we are going to use this shortcut. The shortcut is under root of q1 by under root of q1 plus q2 into r. R is a distance between them, 10. q1 charge is of the 4 microcoulomb. Under root of 4 plus under root of 2. It is going to come upon as 10 whole divided by under root of 2 plus 1. Did we got the same answer? Right. How to apply this shortcut? This is a shortcut to calculate the point where net electrostatic force is 0. The shortcut to calculate the point where net electrostatic force is 0. Right. The net electrostatic force is 0. Okay. The second point we are going to reach it up where net electrostatic force is going to come as maximum. But that thing is different. So under root of q1 by under root of q1 plus under root of q2 into r. The one you are selecting, see, you are having a choice which one you want to select as a q1 or q2. If you're selecting the 4s q1, then whatever the answer is coming, it is with respect to q1. The charge which is at the numerator, the answer that is coming with respect to it. If you're taking 2 into the numerator, then the answer will be with respect to this. Please mind it. This will be, I think, approximately whatever it will come. Okay. So this is a shortcut. Okay. Select Q1, Q2. Okay. Centimeter, or you can say into the meters. Okay. So this is how, right, the net force is calculated. Now here comes the system of the two charges. From this, two kind of questions, right, are asked. Suppose this is charge number 1, this is a charge number 2, and this is a charge number 3. They are placed on the vertices of the equilateral triangle. Question says charges are placed on vertices of equilateral triangle. Superposition principle. What do you need to calculate? Here the distances are being an equilateral triangle, distances are. The question says calculate, first thing, step 1. Calculate the resultant force of any of the charge. Suppose we are calculating the resultant force on 2. See, mark my words. Force on 2, resultant force. It means this is force acting on 2s because of 1. This is force acting on 2s because of 3. Angle between them is 60 degree. This is another way to calculate the resultant force. As the distances are, charges are of same magnitude. You can say charges are same. Identical charges. Then the magnitude of this is also going to be F, magnitude of this is also going to be F. How we are going to calculate the resultant force? The resultant force is through vector addition. F square 2 F square cos of 60. The resultant force is going to be under root of F square. The resultant force, it is going to be under root of 3 of F. Somewhere like this way. Now my question comes. The question of an equilibrium. This question is easy. 3 charges are kept. Okay, there is a possibility that charges may be identical or unidentical, but same concept we are going to use, whether they are going to be identical or they are. If you want to represent this into the vector form, you can do that. Okay, I can represent this F2 of 3, that is equal to negative F of I. Okay, I can resolve this into the two components, right? This will be F, right, cos of, this one is 16, F sine of 60, and this is F cos of 60. I can represent this into the vector form, and even I can replace it. See, resultant force on the 2 into the vector form, that is resultant force 2s because of 1 plus resultant force 2s because of 3. I can replace this part and this part into the vector form in this equation, and even I can resolve. Both are the same procedures, right? Okay, through both of those procedures, you are going to reach up to the same answers. Through both of those procedures, you are going to reach up to the same answers. But this is what somewhere we are used to it. And immediately, see, the purpose of solving those sums into the physics, that immediately you should get a click, okay, and it can be resolved within a minute. So for that reason, this is the second simplest way. Okay, this is an actual. Forces always occurs in pair. Then how is it's possible that this resultant force is individually occurring? Is it not possible? And how it is possible conceptually if the 3 charges are placed on the vertices of the equilateral triangle? See, again I am going to tell you all. If 3 charges are placed, suppose this is charge, and this is charge, are placed on the vertices of the equilateral triangle, right? How it is practically possible that they are going to be stationary? with respect to the centroid, there exists an equilibrium. With respect to the centroid, there exists an equilibrium. See, here the resultant charges are there. To balance, sorry, here the resultant force is there, right? To balance the resultant force in question, right? See, I told you all the Coulomb's law is only applicable for the stationary charges. You told, sir, some students might be having question into their mind. Sir, you told us that Coulomb's law is only applicable for the stationary charges. And how it is possible? I told that they are moving. I told you all Coulomb law is only applicable for the stationary charges. It doesn't mean that, okay, the equilibrium conditions, right, never exist. Okay. Suppose these charges are moving into the circular path like this way. In question it is mentioned charges are present in the vertices, right? They are moving on circular path. As of force of attraction. As of mutual force of attraction. Then there exists equilibrium condition. Against this resultant force with respect to the center, we are having the centripetal that balances the situation. There is a possibility. There is the possibility, right? But students generally used to confuse onto that. Okay, but don't get worried. Okay, the questions only from this, right, they come up into an examination. Okay, that is for the different purpose, but don't get worried. Again, we are going to see into this concept. 4 identical charges are placed on the vertices of the square. It seems to be rectangle, but it is just a human error. This is nothing else but a square. It seems to be rectangle, but this is nothing else but a square. Okay, just hold on here. Question says calculate the resultant force acting on us because of any one reference. Suppose we are selecting as 2. Calculate the resultant force on second charge. This is force acting on 2 as because of 3. This is force acting on 2 as because of 1. Force acting on 2 as because of 4. Now we need to calculate. Into the previous case, we were about to calculate the resultant of the 2 vectors. So as of that reason, this method was easy. Right? This method was easy. But now what we are going to do, we are going to calculate the resultant of the 3 vectors. So without any hesitation, just write it down, the resultant force acting on 2. Okay? So that is equal to force acting on 2 as because of 1. Plus force acting on 2 is because of 3 plus force acting on 2 is because of 4. You can do that. You can follow the previous procedure also. First of all, you can calculate the resultant of 2n1 and 2n3 because they are same in magnitude. As this distance is A or R, right? This distance is R, na? Okay. So they are same in magnitude. They are same into the magnitude. So it happens. They are same into the magnitude. So first of all, you can follow that. You can just find out the resultant of this 2 and you can just evaluate it with the third one. Okay, but that will consume a lot of right time. So rather than that, we are directly moving on to this approach. F2 of 3, that is equal to negative of F of I plus F2 of 1, that is equal to negative F of J. This thing you all aware of, that this is an origin. Whatever the charge, whatever the reference charge you are selecting, consider this as origin, right? This force is in the left direction, so that's why according to the sign convention. I told you all into the victory badge also, I told you all into that champions badge also, that all of those sign conventions are in the entire physics like this way. Negative of I, plus of I, plus of j, negative of j, right? So this is negative f of I, negative f of j, right? If I'm talking about this f2 of 4, okay, then one component is, okay, see now, f2 of 4, that is equal to k q2 q of 4. All charges are identical. So this is going to be r root 2 whole square, r root 2 whole square. So this is going to be f by 2. Right? This is going to be f by 2. F is what? K q square by r square, that is equal to f. Right? So this is going to be f by 2 because all charges are identical. Consider all charges as identical. Now what happens here? If I'm resolving this component, the magnitude is f by 2. Right? Okay. Now this is making 45 degrees. So it is f by 2 cos of 45, f by 2 sine of 45. So I can resolve it as f by 2 cos of 45, that is j, right, negative f by 2, right, sine of 45 into I. So this is negative f of I, negative f of j, negative, you can say f by 2 root 2 of I, negative of f by 2 root 2 of j. Now we need to resolve this stuff. It's negative of I, 1 plus 1 by 2 root 2 of I, negative of f, 1 plus 1 by 2 root 2 of j. Right. This is the resultant force of 2 into the vector form. Further, you can find out this magnitude and everything. We are not moving on to that part, but further you can find out those magnitude and everything. Okay, so this is how, using the Coulomb's law, the resultant force is calculated. Now let's move on to some of the different examples. A charge q is placed at the center of the line joining between the two equal charges. Two equal charges are there, capital Q, capital Q. Alright. The charge small q is placed at the center. Right? Charge small q is placed at the center. The system of the three charges will be in equilibrium. In equilibrium conditions you have understood into the mechanics. Right? But we will understand this into the detail, right? Into the practice based question, but it's okay. It's nothing else where net force or the net acceleration of the particle is getting 0. Translational equilibrium. What we need to calculate, see, this only happens if I am saying this system is in equilibrium anyhow. The resultant force on anyhow, the resultant force, oh, I'm sorry, this is plus q, this is plus q, somewhere small q is kept. Right? Okay. The net resultant force on the each particle is 0. Okay. Sorry for the interruption, right? Equilibrium means what? Equilibrium equations only occur when the net force on each is 0. Then and then the equilibrium equations occur. Suppose if I am talking about the first particle, the net force on the one is 0. Right? So this is equivalent to k, q, capital Q whole divided by, it is in the center, na? Then we can say it is as r by 2. So it's r by 2 whole square plus k q square whole divided by r square. Now this is going to be 0. Now we need to resolve this stuff to find the value of small q. Very simple thing. Maximum number of the questions are going to come upon from the equilibrium only. Right? So here what happens? K, Q, capital Q whole divided by R square by 4. negative, that is equal to kq square whole divided by r square. R square is going to get cancelled, 1q is going to get cancelled, k is going to get cancelled, q is equal to negative q by 4. Very simple equation. This is the perfect answer for this specific. Equilibrium, net force 0. If you have seen the lectures of the victory batch, the champion series, in which the thousands of times we screamed equilibrium, equilibrium, translational equilibrium, rotational equilibrium, directly associated with the net force or the result. Two particles each of mass m and charge carrying q are separated by some distance. Again, see, if they are equilibrium under the mutual force of mutual gravitational and electrostatic force. What does it states? Two charges are there. One having mass m, charge q. Mass m, charge q. They are separated by the distance r. They are in equilibrium condition under, mark my word, see, equilibrium conditions under mutual gravitational and electrostatic force. Gravitational, it means that magnitude of the gravitational force is matching the magnitude of the electrostatic force, k q1 q2 by r square, g m1 m2 whole divided by r square. R square is going to get cancelled. What we need to calculate? We need to calculate, see, charge to mass ratio, specific charge. This thing we have discussed into the previous lecture. We have to calculate the charge to mass ratio. So here q square by m square, that will be equivalent to under root of g by k. So q by m, that will be under root of g by k. So this is going to come approximately into the order of 10 to the power minus 10. B is the perfect answer for this specific question. Some value it is going to come upon as directly proportionality sign, we can't make it as k into or n into 10 to the power minus 10. We need to calculate the order, right? So equilibrium conditions into the resultant, the electrostatic force is quite helpful. The point charges are placed on the corner of the equilateral triangle. As of that, the electrostatic forces are acting. Okay. Now let's keep it that part only. Okay. Okay, let's see this. It's okay. 3-point charges are placed at the corners of the equilateral triangle. Assume that electrostatic forces are acting. See, we have seen this sum Q, Q, Q. They are kept right on the vertices of the equilateral triangle. The system is in equilibrium if the charges have same magnitude but not same sign. Wrong. For, see, there is one result. For regular polygons, for one new note, kindly note this with the right into your book. This is a quite important. For the regular polygons having identical charges on their vertices, right, having identical charges on the vertices, the net force on the center is always 0. This is a new result. The net result, the net force on the center is always 0. Okay. So for that identical charges, it means should be same in magnitude and sign. So if they are in different magnitude and in different signs, right, so whether they are going to attract each other, obviously not whether, but they are going to attract each other, and equilibrium conditions is not attained. Equilibrium conditions right is attained only when some net resultant force is acting, right, and right, see, first of all, at the center point the resultant force is 0. But if I'm talking about the equilibrium condition, then there exists some kind of then electrostatic, the resultant force, and opposite to it we are having right, some kind of the centripetal or any else force that is balancing the situation to make the entire system in equilibrium. So first is a wrong statement. they all should be identical. It is compulsory. The system will be in equilibrium if charges have the different magnitudes. Wrong. System will be in equilibrium if charges rotate about the center. There is a possibility. See, right? There is the possibility. Okay. Now see, some of the sums are there, right? That will be included into the notes, right? Those will be included into the notes, right? You can just, I have kept this for you all. Okay, and this will be included into the notes, but I think Coulomb's law, that much is enough. If we are again taking more than 1.5 hours for this, then students are going to kill me up. Sir, what is this? And okay, I think that much is enough for today. We have seen the Coulomb's law, right? I will be waiting for all of your response beneath the video regarding this. Don't get worried. The very critical and mixed concept based questions on the Coulomb's law we are going to cover up into the practice based question. Today we saw 5 to 6 sums, 7 sums, right? Okay, some of the my example I also showed you all, but it's okay, it happens, but it was relevant to the Coulomb's law. Okay guys, it's time to go again. We are going to come back tomorrow. Tomorrow it will be the concept of electric field and its relevant equations. For the single charge, for the n charges, its vector form, and for all of those equations and the respective derivations we are going to see. So guys, kindly be present tomorrow. Okay, it's time to go. This is Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste. Hope so you like this lecture. Please be attentive. Please be regular. Have note and a pen. Always note all of those mandatory things. Okay, today it was a very simple part, so we didn't move on to the dissections of the NCERT, but slowly it will come up. Okay, so guys, this is Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side, bacha ji. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Bye bacha.